Okay, so my presentation will be also in English. I will talk about machine learning method for stress detection with an EEG device. This work is done at the Department of Intelligent Systems here at the Gjoreski Institute, and I'm Martin Gjoreski, and the work is done under the supervision of Professor Matjaž Gams and Dr. Mitja Luštrek. So previously my colleague was talking about how stress can be detected using some wearable device that provides physiological data such as heart rate, sweating rate and so on. And now I will talk about detecting stress with an EEG device which monitors the electrical activity of the brain. So now we all know how we feel when we are under stress. Our heart rate is increasing, our sweating rate is increasing, and skin temperature also is changing, and so on. So these are all this is part of the fight or flight response of our body. However, all of these signs that we are feeling actually are guided by the brain. So we have this is the stress response system here. So we have the hypothalamus, which sends which is using stress hormones to guide the adrenal glands, which are extracting we are secreting the cortisol and adrenaline, which are producing all the changes in our body, which is called the fight or flight response of the human body. So if our brain is doing all of this to the human body, then it is safe to assume that we can spot some electrical changes in the brain activity. So this is something from the related literature. It is fairly known that when, for example, when we are so here in this column we have the mental states of the human. So when we are sleeping, then our brain works in the delta frequency bands, or when we are relaxed, for example, when we are not we are tranquil, then the brain works in the alpha frequency band, whereas when we are in high alertness situation, the brain works in the high beta frequency. So if we try to translate this into some kind of stress levels, we would get something like this. So when we are under low arousal, then the brain works in the low frequency bands, and when we are under high arousal, then the brain works in high frequency bands. So this is the method that we are proposing for stress detection. So we have raw EEG data that is collected with a commercial EEG device, and then we are filtering the raw EEG data. Then we are performing segmentation of the data. Then we have feature extraction step, and then we are using machine learning algorithms to learn some kind of patterns from that EEG data. The machine learning algorithms, or the model that is learned with the machine learning algorithm, is predicting whether the person is under stress or not. Now I will go through each these stages into details. So in order for us to develop a stress detection method for using machine learning algorithms, we need some kind of data. So for that we conducted stress-inducing experiments here at the institute, where we managed to get 21 participants, and for each session lasted for about 35 minutes. So thus we get 35 minutes multiplied by 21 participant raw EEG data. How the subject were supposed to solve mathematical tasks under time and evaluation pressure. This is a standardized stress-inducing experiment. So we also use it in our we also use it as our approach for inducing stress. The EEG device that we use is commercial EEG device. Here the subject is wearing on his head, which is one-channel EEG device. Provides raw EEG data with frequency of 512. Then also it provides frequency power bands, data for the which is data from the different power bands of 7 or 8 power bands. So those alpha, beta, theta, delta, and also it provides data which is extracted from. They're having, let's call it a soft sensor, which provides attention data and meditation data, and also the EEG device provides data about the blinks, the blinks of the eyes of the subject. Throughout the session, several questionnaires were filled, and these questionnaires were used to label the data. So the questionnaires are used as a ground truth when the subjects are under stress and when they are not. And here we can see that before the experiments, the anxiety level or the stress level is around 11, whereas at the end, medium and in the heart level, throughout the experiments, the anxiety level is increased to 14 and 13. And here we perform statistical tests, and this difference is statistically significant in the in the questionnaires. Now I will present some of the raw data that the device outputs. So the first graph is the raw EEG data. Then we have the data from the soft sensors, or the blinks per subject. Here is one session, so it's 1400 minutes. Seconds, which is around 30 minutes, 40 minutes. So we have the blink intensity. This is the attention. For example, for this particular subject, we can see that there is a slight increase in the attention of the subject, and here this is the data for the meditation. Or if we plot the average level of stress which was extracted from the questionnaires, it would look like this. So here we have, before the experiments, we have some initial data, then the subject is solving one part of the mathematical task, then the second part and the third part, and we can see that the anxiety level increases. That was the raw EEG data that we are getting. Now I will talk about the filtering method that we used. So here on the why we needed to filter the data. For example, this here is the raw data for the first band, for the alpha band, which is not filtered, and we can see that there is a lot of noise in it. So and the graph here, the upper graph is the filtered data. The method that we used was Turkish method for detecting. First we needed to detect outliers and then to replace them. For detecting the outliers, we use Turkish method, which is a statistical method and uses interquartile range for the data, and the detected outliers are replaced with average values of the neighboring samples. So after the filtering data, after filtering the data, it was segmented. Here we use different windows lengths. So we performed experiments with window length of 1 to 4 minutes. I will show the results at the end. Then after the data segmentation, from each window we extracted features. The features that we extracted, so the features were extracted using statistical functions such as mean, variability, quartiles, quartile deviation, and power of the signal. Also, we performed a regression analysis for each window, so the intercept and the slope of a fitted regression line, and also we calculated numerical statistics such as blinks per second, significant blinks per second, and so on. So after the feature extraction, we already have the data ready to perform machine learning experiments. So we performed experiments with several machine learning classifiers, machine learning algorithms. So the majority, here we have the majority class, then the naive Bayes, boosting, J48, KNN, SVM, bagging, and random forest. On here, each column represents the length of the window which was used for extracting the features. So we have 30 seconds, 1 minute, 2 minutes, and 4 minutes. And the numbers here represent the accuracy of each of the models. Here, these experimental results are for tenfold cross-validation. So the highest achieved accuracy for detecting stress was by random forest, which is 71, and it is around 19 percentage points higher than the majority class. And now I will conclude. So here I presented a study for stress detection using a one-channel EEG device. We performed experiments in laboratory conditions with 21 subjects. The highest accuracy is 71%, and these here are the limitations of the method that we are proposing. So the experimental results are for a tenfold cross-validation, which means that we have the models are not actually the models are subject specific, so we need to work on a general model. Also, well, we saw that there is the data is quite noisy, so probably we will need to use some more advanced technique for denoising the data, and also to maybe to include some more advanced features in the machine learning process. That was my presentation. If there are any questions, I would like to answer.
Thank you. Questions?
Here, how did you choose this time intervals of half minute, 1 minute?
This was like only for the experiment. So we wanted to check how the length of the window from which we are extracting features is influencing the accuracy of the classifiers. So since one experimental session was lasted like 15 minutes, and in those 15 minutes we had 3 sub-sessions which lasted for 5 minutes. So that's why we went from half minute to 4 minutes. So that was our logic for this, for the time intervals.
Actually, I have a question about this same slide. So by the design of the experiment, one would expect that longer intervals would have the same stress. And if memory serves me, in earlier experiments with physiological sensors, it was also the case that longer intervals were better for stress detection. So do you have some explanation why shorter intervals work better here?
Well, it's not really. Why do you think that short intervals work? Only for this, for the 4 minutes. Is that what you're? I mean, for this figure, it's not completely obvious to me that short intervals work better. I would say that the length of the interval does not influence the accuracy of the model much.
Well,
that's what I would say.
You're probably right. The coloring kind of makes this impression, but in reality, the differences are pretty small. Yeah, you're right.
I have a question about how the cross-validation was done. So was the one person, person left out?
No, it's a tenfold. So all the data is mixed and then randomly sampled. So it's actually, so it can happen that there is data from one subject in the test and in the training phase. So that's why I said that it's subject specific. This approach is subject specific.
Okay, so when you do this windowing, how do you do this prediction? So is the windowing length different for the feature extraction than from the?
No, everything is the same. So the windowing is done prior this sampling of the data for.
Okay, I have 2 questions. Like the first would be, you've taken for the ground truth, you have taken the questionnaires, right? So this is probably questionable because it's known that surveys are not reliable, that people do not understand the same. I mean, they do not answer the same thing as they were questioned. It's rather unreliable baseline technique. So maybe, I mean, you have like eye movement tracking or stuff like that, which might be more reliable, and you might get better results because you're inferring some noise in here.
Well, I wouldn't say that eye movement would be more reliable for as a ground truth for stress detection. Well, this questionnaire that we use is standardized questionnaires, which is so the way that these questionnaires are standardized, on one hand they're performing cortisol analysis, and on the other hand they're having the questionnaires, and then they're checking the validity of the answers of the questionnaires and the cortisol. In terms of stress, if there is increased cortisol level, then probably the stress level is increased in the subject, and that's how these questionnaires are validated. So this is straight rate anxiety questionnaire for.
Well, but there's some inconsistency if you look at your results, right? So the hardest questions were less stressful than the. So we have 13.8 and 14.05. So
the thing is that
should be larger than 14.5.
That's true, but this here is the end of the session, and the subject is feeling a little bit more relieved than he was prior the hard session. So that, at least that is my theory.
And also you get used to the.
Was part of the stress test. At the end, you get a bit used to it. It's not a stressful anymore, even if the questions are hard.
Why didn't you use the blood pressure?
Well, actually, okay, if we see this picture in detail, so we have the EEG device here, we have a wrist device. So actually, we are performing all kinds of tests. Here, I'm focusing on the EEG device. Otherwise, yes, we use also the physiological signals for these experiments to detect stress, which is more precise. The approach that we have with the physiological sensors is more accurate, and it's general. It's not person specific. And also we have voice. So the next one is voice analysis for stress detection.
My suggestion would also be that I've still listened to a paper which deals with time series, and it turns out that some modification to random forest is called random shapelet forests are much more accurate.
Okay, thank you. I will check for it.
One more question here.
It's a good one. So I know that you have done experiments with the wristband and now with the EEG. So according to your experiments, the wristband works better for stress detection, right?
Well, I also have to admit that I worked on like 1 year on detecting stress with wristband and like 1 month on detecting stress with an EEG device. So maybe there is still some improvements for the EEG approach.
Yeah, definitely you should do frequency domain analysis. I think it makes a lot of sense on EEG data.
We have frequency domain. These power bands are actually the frequency domain.
But also you can do on the raw data.
Yeah, we can.
Okay, let's thank the speaker again. Zdaj, naslednja predstavitev ne bi bila od Miha Mlakarja o prepoznavi kliničnih udarcev, ampak predavatelja